In today's class, we will learn about very basic concept of digital circuits or digital electronics, that is about logic gates. A logic gate is a logical circuit which makes logical decisions, but physically it is an electronic circuit comprises resistors, diodes, transistors. In logic gates or logical circuits, there we see two logics or two logical values which are 1 and 0. But it is not mandatory that 1 represents logical high value and 0 represents logical low value. No, it depends on logic systems. In digital system or logical circuits, we have two types of logic systems, positive logic and negative logic. If we maintain or we follow positive logic system, then we have two types of logics, high and low. And again, in negative logic system also there are two types of logical values, high and low. But what is the difference then? Suppose if we have two voltage levels in the circuit such as 5 volt and 0 volt, then we know that 5 volt is greater than 0 volt. So in positive logic system, logic high will be mapped with 5 volt, and logically low, that level will be mapped with 0 volt. But in that circuit, suppose if we have two voltage values such as minus 5 volt and minus 2 volt, then we know that minus 2 volt is greater than minus 5 volt, because minus 5 is more negative compared to minus 2. So under positive logic system, minus 2 volt will be mapped with logical high value and minus 5 volt will be mapped with logical low value. And this case is reverse in case of negative logic system. So if we follow negative logic system and if we have in the circuit two voltage levels again such as 5 volt and 0 volt, then logical high will be mapped with 0 volt and logical low will be mapped with 5 volt. Similarly, again if we have minus 5 volt and minus 2 volt, these two voltage values in the circuit, then again minus 5 is less than minus 2 as far as value is concerned. So in that case, minus 5 will be mapped with high value and minus 2 volt will be mapped with logical low value. So this is how it happens, or this is how it depends on the logic system, means which value will be mapped with logical high and which value will be mapped with logical low. Now we have mostly in our logic gates, we will see that there are two inputs or more than two inputs. There is one specific gate, logic gate, where we have only one input and that is NOT gate, and that will be explained in more detail little later. And always from those logic gates there we have only one output. Among the logic gates that we have in digital circuits or digital electronics, OR and NOT, these are basic gates, and NOR and NAND, these two are called universal gates, because using this NOR and NAND we can represent any other gate or any other digital circuit, or we can implement any Boolean expression. Next we will see the functionality of NOT gate. First we will understand the operation of a NOT gate by using this simple electrical circuit. In this electrical circuit, what we can see is we have a voltage source, DC voltage source here. We have a switch here which is open, and we have a bulb here. Now when this switch will remain open, what will happen to this circuit? The current which will be supplied by this voltage source, the whole current will be flowing through this path or through this bulb, and no portion of that current will be flowing through this path as the switch is open. So we have an open circuit here, so the bulb will glow. Now we will understand this better by using this relationship. So when the switch is open, if we map this as logical 0 value, so it will be 0. Now when the switch is open, bulb is glowing, right? So if we map the glowing of this bulb as logical 1, and that we take as the output of this electrical circuit, so on means logically it is 1. So when the switch is open, the bulb is on. Now what will happen when we'll close this switch? When the switch will be closed, there will be a closed path here. So the current which will be supplied by this voltage source, the whole current will be flowing through this path. Why? Because the resistance of this path is 0. So no current will be allowed to flow through this bulb, as the bulb has its specific resistance. So the whole current will be flowing through this shorted path and the bulb will not glow. So if the closing of this switch, if we map this with as logical 1 at the input side, then bulb will not glow. And that if we map with logical 0 value, so what relationship we can see here, that when the input is logical at logical 0, the output is 1, and when the input is at logical high value, then the output is at logical 0 value. So it is just the reverse. When it is 0 at the input, it is 1 at the output, and when it is 1 at the input, the output is 0. So this is the operation of NOT gate. It is actually a complementary relationship between input and output. This is the circuit symbol of NOT gate that we mostly use, and this is also another circuit symbol of NOT gate that we sometimes also use. So now suppose if we have input that if we represent by A, then at the output side, the output, if it is Y, then output will be A prime, or we can write A bar. And in the second circuit symbol that we have here, if the input is A, at the input side what we can see here is we have a bubble. The bubble represents the complement. So at the input side itself, the input is complemented. So A becomes A bar now. So Y is again here is A bar. So whatever is the circuit symbol, the finally the output will be the complement of the input only, and that is how NOT gate works. And this is the truth table of NOT gate. And what is truth table? A truth table is a means to describe how the output of a logical circuit depends on the logical levels of the inputs. So what we can see in this truth table is, when the input is 0, output is 1, and when the input is 1, the output is 0. These are not the actual values, these are the logical levels, logical low and logical high. Next we will understand the operation of AND gate. Now again we will understand by using this switching circuit where we have two switches. As we know that in case of NOT gate we have only one input and one output. In case of AND and other gates we have at least two inputs. That's why we have used here two switches. So switch here represents the input. So in this circuit what we can see, again we have a DC voltage source, we have two switches, and we have a bulb where the bulb represents the output. Now when both the switches will remain open in this circuit, then what will happen? When these switches will remain open, both the switches, then no current will be flowing through this path or through this bulb, because there is an open circuit. So even though the voltage source is there, the bulb will not glow. Now again if we map the relationship between these switches and the bulb, and again if they have the same meaning, means opening of bulb if it is mapped with logical 0 and closing as 1, and glowing of the bulb is mapped with logical 1, and when the bulb will remain off, then if it is mapped with logical 0, then when both the switches are open, that means 0 and 0, then the bulb will remain off. So it is also at logical 0 when one of the switches will be turned on. Now suppose if we close switch 2, closing means we are connecting this path, but what will happen, since the switch 1, this still remains open, so this portion of the circuit still is open and the whole circuit is not yet closed. So even though the voltage source is there, the bulb will not glow because the whole circuit is not yet complete path or is not closed. So closing of switch 2, if we map that as 1, but still since switch 1 is open, so that will be mapped with 0, and the bulb will not glow, so that will be mapped with 0. Now what will happen if we now suppose close switch 1, and if we still the switch 2 remains open, then again the circuit is not yet closed, not yet complete, so bulb will not glow as no current will be flowing through this path. So closing of switch 1, if we map that with logical 1, but still switch 2 is still open, so no current will be flowing through the bulb and bulb will still remain off. Now what will happen if we close both the switches at a time? Then both the paths are closed and the whole circuit is also complete or closed. So at that time, the current which will be supplied by this voltage source, that will be flowing through this bulb and bulb will glow. So closing of both the switches means 1 and here also 1. So bulb will glow means that is also 1. So what we can understand is, if both the switches at a time they are off, then only the bulb will glow in that circuit when the switches are in series. But if one of the switches is open, then the bulb will not glow, and that is the phenomena, that is the operation of AND gate, and that we will understand by its truth table and also circuit symbol. So here what we can see is, here we have two input AND gates. So if two inputs we represent by AB and the output if we represent by Y, then the expression or the relationship between inputs and output of an AND gate that we represent, that is by Y is equal to A dot B or A and B, that we say. Now this is a circuit symbol where we have three inputs and one output, and this is a circuit symbol where we have again two inputs, one output, but both the inputs and output they are in negative form, they are in complemented form. So if the input, actual input A, if they are A and B, that means when it is negated or when it is complemented, then at the input side it will become A bar and it will become B bar. So what will happen, A bar, and then we have here this symbol is a symbol of OR gate. So it will be A bar plus B bar. OR gate I will discuss little later. So A bar plus B bar, then as per De Morgan's theorem we know that will become A B then bar, A and B then whole bar, whole complemented of that AND operation, A and B. And here at the output side also we have another bubble, another complemented form. So it will become at the output side it will be actually AB bar, and of that again one bar because of this bubble. So finally it will become AB only. I mean AB means A and B or A dot B. So though it is it looks like a OR gate, but this will finally work as an AND gate. And truth table of AND gate is like this, what we have already seen for this switching circuit. So when both the inputs are 0, then also the output is 0, means at logical low level. And when one of the inputs is 0, then also the output will be at logical low level. And only when both the inputs are at logical high level, means 1 1, then only the output of that gate will be at logical high level. So this is the concept of operation of AND gate. So we have to remember in case of AND gate that when both the inputs are high, then the output will be high. Otherwise, if one of the inputs is low, then the output of that gate or that circuit will be low. And no need to say, if both the inputs are at low level, then the output will be always also at logical low level. Next we will understand the concept of OR gate. Now again we have this switching circuit where, since OR gate, so at least we will be using two inputs. So here again we are using two switches, and this time the switches are connected in parallel instead of series, what we have seen in case of AND gate. And again since we have one output in the logic gate, so here we have used one bulb which we know that represents the output. So again we have here a voltage source. Now this will understand by this relationship between switch and bulb, and the opening and closing of switch and glowing and not glowing of the bulb, they have the same meaning that we have seen earlier. Now when both the switches of this circuit are open, what will happen? Both the switches are open means through no path of this circuit current will reach to this bulb and bulb will glow. No, since this both the switches are open, so the whole circuit will not be a closed path, will not be a closed circuit. So Even though there is a voltage source physically, no current will be flowing through this bulb, and bulb will not glow, it will remain off. So when both the switches are open, means 0 0, the bulb will not glow, so it will be at logical low value, which is 0. Now suppose if we close S2, means the second switch, then what will happen when we are, since these switches are connected in parallel, so if S2 is closed, then the circuit will get a closed path through this switch, and the current which will be supplied by this voltage source will be flowing through this bulb, and bulb will glow. So what we understand here, that when the switch 2 is closed and switch 1 still is open, then the bulb is glowing, and that means output is at logical high level. Now if it happens thus the opposite, means if switch 1 is closed, that path is closed, and switch 2 is open, then what will happen? Again, since these switches are connected in parallel, so a closed path will be formed through this S1. So current which will be supplied by this voltage source, that will get a closed path through this switch, and that will be flowing through this switch as well as this bulb, and bulb will glow. So we understand here that when switch 1 is closed, means it is at logical high value, at logical high level, and switch 2 is at logical low level, it is 0, then the bulb is glowing, that means output of that circuit is it at logical high level 1. Now what will happen when both the switches are closed at a time, at the same time? So no need to say again, if both the switches are closed, so the whole current will be flowing through this through both the paths, and again the whole current will be flowing through this bulb, so bulb will glow. So when both the switches are closed, means 1 1, the bulb will glow, and that will be output of the circuit will be at logical high level. Now if we see the truth table of this OR gate, then that will be same as what we have seen here. This is the circuit symbol of OR gate. So it is a two input OR gates where A and B are inputs, and if we represent output of this OR gate by Y, then the relationship between input and output is written like this: Y is equal to A plus B. So OR operation, basically it is an addition operation of both the Boolean variables, we can say. Now this symbol is the OR gate for three inputs A, B, C, and again output is Y here. And this is a symbol we can see here. Apparently it is an AND gate that we have seen just before this OR gate. So if the inputs are A, B here, and if the output is Y, will it be an operation of AND gate or OR gate? That we have to see. Now A, and we have here two bubbles, and at the output side also we have bubbles. So A basically will work as A bar at the input side, so A bar, and B also will work as a complemented of B because of this bubble that we can see in this circuit symbol, so it will be B bar. So between A bar and B bar there will be AND operation. So AND operation means, by De Morgan's law, we know that will be A plus B and then whole bar, and at the output side we have another bar, another bubbles, and so we will get the complemented value of this A B bar. So it will be finally A plus B only. That means finally we will be getting the output of OR operation only. So this is another symbol that we use for OR gate. Now this is the truth table of OR gate that we have already understood. So when both the inputs are 0, then output will be 0 at logical low level. When one of the inputs is at logical high level, then the output of that gate will be at logical high level. And when both the inputs are at logical high level, then also the output of that gate will be at logical high level. So in case of AND gate, what we have seen, what we have learned was, when both the inputs are at logical high level, then the output of that circuit will be at logical high level. And here in case of OR gate, when both the inputs are at logical low level, then only the output of that circuit will be at logical low level. That means when both the inputs of that gate will be 0 0, then output of that gate will be 0. Otherwise, if one of the inputs is 1, then the output of that gate will be 1. Next, we will understand the operation of NAND gate. It sounds like and then one more NOT. Basically, NAND is one AND followed by one NOT gate. So and then from that NOT, this N comes. And this is the circuit symbol of NAND gate, where we can see this represents basically AND gate, where we have two inputs. If we have A, B, and if output is Y, then what we can see is after and there is a bubble, and bubble represents the complemented form. So output will be A and B, then complement of that operation. So we can say A and B and then not of that and operation. So finally it will be and plus not NAND. Now this is the truth table of NAND gate. What we can see here, if both the inputs are 0 0, if both the inputs are 0 0, in case of AND gate, what happens? It is 0. And then if it is followed by a NOT gate, then what will happen? Then 0 complement of 0 will become 1. Now when both the inputs are, one of the inputs is 0 and one of the other one is 1, then what will happen in case of AND operation? So 0 and 1, it will be 0 after performing AND. Then if we perform the complement of that 0, then it will become 1. Now if we swap the status of both the inputs, then 1 and 0, then again it will become 0 after performing AND operation. And then if we take the complement of that value, means 0, means if we perform NOT operation, then that will again become 1, and that's what it has been written here. Now when both the inputs are 1 1, so 1 and 1, then as per AND operation it will become 1, and when we will perform NOT operation, then complement of 1 means it will become 0, and that's what we can see here. So the operation of NAND gate is what? So when both the inputs are 1, means when they are at logical high level, then the output is 0. Otherwise, if one of the inputs is 0, means at logical low level, then the output of that gate is at logical high level, just opposite to the AND gate or complement of the result of AND gate. And this is the symbol of 3 input NAND gate, A, B, C, and here we can write Y. So here Y will be basically A and B and C, and then complement of that. And this is the circuit symbol of again NAND gate, where we can see apparently it looks like OR gate, and we have two complemented inputs. So here if the inputs are A, B, and we have already at the input side we have the complemented form. So A bar and B bar, these are actually the inputs, and we are performing OR operation. So what will happen? A bar plus B bar, as per again De Morgan's law, it will be A B, or A and B then bar of that. So output basically will be A and B and then complement of that. So that means it is NAND operation only. Now next we will see the operation of NOR gate, and again this is the symbol of a 2 input NOR gate, where A, B are inputs and Y is the output. This is the logical expression of 2 input NOR gates, where Y is A or B and then complement of that. So first we will perform OR operation, and that will be followed by NOT operation. Now this is the truth table of NOR gate, where when both the inputs are 0, then what will happen? Both the inputs are 0 means 0 plus 0. So as per OR operation, that will become 0. And now if it is followed by NOT operation, then that will become 1. And that's what we can see here. Now when one of the inputs are 1, so as per OR operation, that becomes 1. And when that is followed by AND operation, then complement of 1 means that will be 0. So here 0. Then again if we swap the status of the inputs, so again the output of OR operation, first operation is OR, so that will become 1, and when we will take the complement of 1, that will become 0. Now when both the inputs are at high level, logical high, then output as per OR operation will be 1, and then when that will be followed by or not operation, then it will become 0, and that's what we can see here. So what we can see here, when both the inputs are at logical low level, then only the output of that gate will be at logical high level. Otherwise, if one of the inputs is at logical high level, then the output of that gate will be at logical low level, just opposite to OR gate, or we can say complement of the OR operation. Now this is the circuit symbol of 3 input NOR gate, where A, B, C are 3 inputs and Y is the output. So we logical expression we can express this way: Y will be A plus B plus C. So first OR operation between these 3 inputs or 3 Boolean variables, then followed by NOT operation. And this is the circuit symbol of again of a NOR gate, where A, B are inputs and Y is the output. Apparently it looks like an AND gate, but if we see at the input sides, then they have the complemented form. So A will be taken as A bar and B also will be taken as B bar, and then they between them we are basically performing AND operation. And as per De Morgan's law, then it will be A plus B means A or B, and then the complement of that result. So basically it is an NOR operation only. Now next we will see the operation of another gate, which is XOR gate. This is the circuit symbol of 2 input XOR gate, where A, B are input and Y is the output. And this is the truth table of this XOR gate, where the input and output are related by this symbol A. This is the symbol of XOR gate, then B, and logically they are related like this: A then B complement plus B then A complement. So this is how both the inputs and output of an XOR gate is related. Now if we look at the truth table of XOR gate, then when both the inputs are 0, then what will happen? So when both the inputs are 0 0, so as per this relationship, it will be A will be 0 and B bar, B is also 0, so it will be 1, and there is AND operation, then plus OR operation. B is also 0 and A is 0, so complement of A will be 1. So what will happen? 0 and 1, AND operation between 0 and 1, so it will be 0, and from the second term also AND operation between 0 and 1, so it will be again 0, and then OR operation between 0 and 0, so finally it will become 0, and that's what it is written here. Now when one of the input or first input is 0 and the second input is 1, then what will happen? So A is 0, so here it will be 0, B is 1, so complement of B will be again 0, AND operation between two zeros, then we have here OR operation, then B is 1, so it will be 1, and then AND operation, and then A bar, A complement, so A is 0, so it will be, then complement of 0 will be 1. So from here first term we will have 0, then from the second AND operation we have 1, or operation between 0 and 1, so it will be 1, and that's what it has been written. Then first input is 1 and second input is 0, then what will happen? So A is 1 and B is 0. B is 0 means complement of B will become then 1. So AND operation between two ones, then we have OR operation, then B is 0, so here it will be 0, then AND A is 1, so complement of A will be 0. So here finally it will be AND operation between these two values will be 1, and AND operation between two zeros will be 0. So 1, or operation between 1 and 0, so finally it will be 1 only, and that's what it has been written here. And then finally both the inputs are 1, so what will happen? So when both the inputs are 1, then complement of the other input will become 0, so it will be 1 complement and then AND 0, and here it will be 0 and 1, so finally it will be 0, or operation between two zeros, so it will be 0. So what we can see here, that when both the inputs of that gate have the same value, either 0 0 or 1 1, then output of that gate will be at logical low level. So whether both the inputs have 0 or at high level or low level doesn't matter. If both the inputs have the same status, logical low or logical high, then output of that circuit will be always at logical low level. But if both the inputs have the opposite status, one is at logical high level and the other one is at logical low level, then the output of that gate will be always at high level, logical high level, and that is the concept of XOR gate. Next we have XNOR gate, and that means we can understand that XNOR is basically XOR followed by an NOT operation, and symbolically also it is XOR gate. Then we have a bubble at the output side. So inputs, if we have AB, and output if it is Y, then Y will be written as A, and this is the symbol of XOR, then B, and then complement of that XOR result. So this is the expression of an XNOR result, and this relationship between output and input. And this is the truth table of XNOR gate, where when both the inputs are 0, then what will happen? When both the inputs are 0, we have seen previously, when both the inputs are 0, then the output is 0. When both the inputs are 1, then also output is 0, otherwise they are 1. So when both the inputs are 0, as per XOR operation, XOR operation, it will become 0, and then when it will be followed by NOT operation, then it will become 1, and that's what it has been written here. And when both one of the inputs will be 0 and the other input will be 1, then we have seen that as per XOR operation, that becomes 1. So here 1 1, and then when it will be passed through NOT operation, so it will become 0. So that's what it has been written here. And when both the inputs are 1 at logical high level, as per XOR or XOR operation, the output is 0. We have seen there that when both the inputs have the same status, then output of XOR operation is 0. And then when we will perform NOT operation after that, so complement of 0, it will become 1. So operation of XNOR gate is just opposite to XOR gate, means the XOR gate, the output of that, and then followed by a NOT gate. So here when both the inputs have the same status, then output of the circuit of that gate will be at logical high level. Otherwise, if they have the opposite status, then the output of that circuit will be at logical low level. So this was all about the basic operations of all the logic gates that we study in digital circuits or digital electronics. I hope this class was meaningful to you. See you in the next class. Thank you.